The Wilcoxon signed rank test for paired samples. When testing the population average for paired samples, we have a choice of 3 tests. We're going to look at the Wilcoxon signed rank test here. Now this test assumes that the population average differences are symmetrically distributed, i.e. the mean and the median are the same. We can test either for the mean or the median. So this one's the population mean difference, and this one is the population median difference. Any 0 differences are crossed out and not used in the test. Example 1. We have 9 different types of carpet labelled A to I, and 2 different types of glue, or 2 different types of adhesive. And we're going to use a Wilcoxon signed rank test using a 5% significance level to investigate whether there's any difference in the average fixing times for these 2 adhesives, for a difference, so a two-tail test. So H0 and H1 in terms of the population mean difference, and to work out the differences I'm taking the values for adhesive 1 and doing that minus the value for adhesive 2 in that order. The order doesn't make any difference for a two-tail test. We could have done 2 minus 1 instead. Okay, so we have our carpet types and then the actual differences, and then ignoring the minus signs we rank these differences. The smallest is rank 1, and then we separate those ranks according to the signs of these differences into positive and negative ranks. So these are the actual ranks, and then you add up the positive ranks, so that's the 1 and the 4, and you add up all of the negative ranks. The smaller out of the 2 values, which is 5, becomes our test statistic. So then we go to the Wilcoxon tables. It's a 5% significance level. It's a two-tailed test. N is equal to 9, so our critical value here is 6. Our test value 5 is less than 6. Test value is less than the critical value. This condition has been met. We're going to reject H0. So our conclusion in context. Part 2. Other factors to consider when choosing which adhesive to use would include the type of carpet used, the type of floor surface, or the temperature. Part B. The advantage of using matched pairs design. And we can see that there is a pair of data here for carpet E. We've used both types of adhesive on carpet E. We've done the same with carpet G. Everything is in pairs in this table. Paired samples. That's what they mean by matched pairs design. What's the advantage of using paired samples? To reduce experimental variation. Different carpets may react differently to both adhesives, so it's better to use adhesive 1 and 2 on each carpet. An alternative but poor design for this hypothesis test would be to use, let's say, adhesive 1 on these carpets, and then we go on to use adhesive 2 onto these carpets. So we haven't used both types of adhesives on all the carpets. Adhesive 1 on A, B, C, D, E, an adhesive 2 on FG, H and I. There is too much experimental variation in this type of design. It's a poor design and one to be avoided. Example 2. We're looking at tread wear measurements of tyres. So how quickly do tyres wear out? And there's two different methods, method A and method B, that can be used to see how quickly a tyre has worn out. And these values in the table are in thousands of miles. So for instance, this value here represents 29,100 miles. And this one here is 33,400 miles. So method A is showing that for tyre 4, the tyre has been driven 33,400 miles. That's what the method is showing. And method B is showing that for the same tyre, the tyre has covered 29,100 miles. So the greater the value, the greater the tread wear on that tyre. So we're doing a Wilcoxon signed rank test using a 5% significance level to investigate whether method A shows greater tread wear, so the values for A should be higher than method B, a one-tail test. So we're looking for the population mean difference to be greater than 0. Another way of coming to these hypotheses is like this. So we could say that for H1 that the mean for A is greater than the mean for B. So the mean tread wear for method A shows a higher value than B. And then putting both of these on the left-hand side, then you've got this. The mean for A minus the mean for B is greater than 0. And this is a difference between the two means. This thing, it's a difference. So then we can say the mean difference is greater than 0. That's where this comes from. So working out the differences, doing A minus B, and there's a difference of 0 which is crossed out and not included, and then ranking the data, so ignoring the minuses on the differences, rank the data, the smallest being rank 1, take into consideration tied ranks like the 7.5 here and here, and then separate the ranks according to the signs on the differences, whether it's a negative difference or whether it's a positive difference. Then add up the ranks. So for the negative values we've got 13.5, for the positive ones 64.5, and the smaller out of those two becomes our test statistic. So 13.5 is our test value. And then going to the Wilcoxon tables in the formula book, 5% significance level, one-tailed test, n equals 12 and not 13, we've crossed this one out, a critical value of 17. Our test value is less than the critical value. If this condition is met, we're going to reject H0. And our conclusion in context.